The Udovich class is a class of weak solutions to the two-dimensional Euler equations. And Udovich theorem is a very famous uniqueness result, and there are very interesting questions about similar uniqueness results in larger classes of weak solutions. Those are the two main problems I want to consider, and my goal is to give, first of all, motivations for the study of weak solutions in this framework. Then I'll present a few recent results in these two very old problems, and finally, if time allows, I would like to talk a bit about flexibility and convex integration. In fluid dynamics. Okay, let's start with the equations. I'm about to write down the Navier-Stokes system. In the Euclidean space of dimension n. And in this course, n is going to be either 2 or 3. And the system is the following. Coupled with the so-called incompressibility condition. So, U is an independent velocity field. It represents the velocity of our fluid flow. P is a scalar field, is the pressure. F, again, is a vector field and is the external body force acting on the fluid. And nu, appearing over here, is a number. It's a positive number in the Navier-Stokes system, and this is the so-called kinematic viscosity. And I will also consider the case, the Vichy case, which formally consists in taking nu equal to 0 in the system, and essentially we drop this diffusion term. And this is called the Euler system. Okay? And the physical meaning of the system is pretty clear. The first equation is nothing but momentum. Force equal mass times acceleration. This one is the acceleration of a fluid particle. This is nothing but the material derivative. This is the pressure acting on our fluid. That's the external body force, you can think of the gravity. And that's just diffusion. This is the force, the friction force coming from layers of fluid. And this is essentially, this term regularizes the system and dissipates energy. The second equation is simply incompressibility. So the fluid cannot be compressed. Okay, let's look at the kinetic energy of the fluid. So, energy balance. So So let us assume for a moment that we have a very good solution to the Navier-Stokes system in Rn. This solution is smooth and it decays at infinity. Now we can check, this is a very, very easy computation, that the kinetic energy at time t, which is nothing but the integral, so if you want, this is nothing but the L2 norm squared, 1/2 of the L2 norm squared of the fluid, is going to be equal to the initial kinetic energy plus a term taking into account the work done by the external body force, plus another term taking into account the dissipated energy due to the friction. So kinetic energy at time t, initial kinetic energy, dissipated energy because of the Laplacian, because of the diffusion, work done by the external body force. And you can check this by simply d dt this term, integrate by parts, and this is what you get. It's really immediate. Now, from the mathematical point of view, what is very important is the following remark. We have a natural class where to look for solutions. This is the so-called energy class. Is the class of velocity fields L2 in space uniformly with respect to time. Intersection L2 time H1x. So this class is very natural indeed. The uniform control with respect to time of the L2 norm is written here. It's nothing but this bound on the kinetic energy at time t in terms of the initial condition and this term depending on the external body force. The control on the H1 norm with H1 norm in space, L2 with respect to time, comes from here, comes from the dissipation. So it is kind of natural to look for solution within this class, and indeed the resolutions, the weak solutions I'm about to introduce, are exactly weak distributional solutions to the Navier-Stokes equation belonging to this natural class. Okay? Maybe another very easy comment. If we consider Euler equations, so the implicit model, we no longer have this term. So we lose any control on the H1 norm. If we assume also f equal to 0, what we get is the exact conservation of the kinetic energy in the case with 0 force and 0 kinematic viscosity. So let me add it as a remark. Euler plus 0 body force, then conservation of kinetic energy. And I want to stress once more that this is a formal computation under the assumption that the fluid is very regular and it decays at infinity. Now, let's talk a bit about the role of the pressure. So let's look at the equation. We are assuming that the velocity field u is incompressible. This means that if you compute the divergence of the first equation, this is going to be 0. This is going to be the divergence of the external body force, so that we can assume to be equal to 0. Or, I mean, worst case scenario is something given. certain function with certain regularity. Here we get 0 as well, because it's again the divergence of u. And here we get the Laplacian of the external body force. And here a complicated quadratic term, the double divergence of u tensor u. So in the end, this gives us an equation for the external for the pressure, an elliptic equation for the pressure, depending only on the quadratic term and the divergence of the external body force. So the pressure always solves this equation. Minus Laplacian, or double divergence of u tensor u plus divergence of f. So if you assume that the external body force is given, if we get the vector field u, then we can find the pressure field by solving this equation. So formally here, what you would write is P equal Laplacian to the power minus 1 div u tensor u plus Laplacian to the minus 1 div f. And to make this rigorous, you can, for instance, write this in terms of the Ritz transform. So this is the most delicate term. So first of all, notice that this is a 0th order operator. You have minus 2 derivatives here and 2 derivatives over here. So this is a 0th order operator applied to u tensor u. And you can express it in terms of the Ritz transform. So this can be written as Ritz transform I, Ritz transform j applied to ui times uj summation over I and j. And Ri is nothing but minus Laplacian 1/2 di is the standard Ritz transform. Okay, so this is just to say, I mean, the precise expression of this operator is not important for the sake of this course. So here the message is that the divergence free condition, the incompressibility condition, and the pressure are introducing some non-locality into the system. But on the other hand, the pressure can always be obtained once we have all the other terms. The velocity field and the external body force. Usually the external body force is given, so the real unknown of this problem is the velocity field u. Once we have u, we compute the pressure. Yeah? Yes, thank you. Yes. But let's now add some initial conditions. So let's look at the Cauchy problem associated to the Navier-Stokes system. So let's assume that the velocity of time 0 is equal to a certain velocity field u naught x given. So my data are the external body force and u naught. Let us even assume a very strong regularity indicating infinity on the initial data. So let's say classical initial data. I'll assume that both u0 and f are smooth and they decay at more than polynomial at infinity. So I'm assuming that for every capital N, for every capital M, for every capital K, if you pick n derivatives in space, m derivatives in time, you can bound this quantity in terms of a constant times some overload decay, some polynomial decay of degree k. It's a very, very strong assumption of the initial condition. And the goal would be solve the Navier-Stokes system, starting from initial condition like this, classical initial conditions, solve the Navier-Stokes system globally in time. So those conditions are imposed at time t equals 0, at least the initial condition is imposed at time t equals 0. I would like to solve the equation for every t positive. And again, the hope is to find the classical solutions, smooth solutions with some decay at infinity. Let me give some definition. So this is taken from the Pfefferman paper about the millennium price problem. So we say that UP is a classical solution to the Navier-Stokes equation with initial conditions U0 and external body force F if U and P are both smooth and globally defined. And the kinetic energy is locally bounded. Okay? When I talk about classical solution, I mean smooth solution with locally bound kinetic energy. As simple as that. And then the natural question is simply, given U0 and F as in this, with this very strong regularity and decay at infinity, is there, or maybe are there, classical solutions? Okay? So we pose classical initial condition and we want to find classical solution. And this is exactly, in dimension n equals 3, this is exactly the millennium price problem. Or at least one possible formulation of the millennium problem. And, I mean, it's not solved. And in dimension n equal 2, it is solved. You can find global solutions. The hard part is dimension n equal 3. Now I would like to explain why it's so hard to find classical solutions in dimension 3. And this explanation serves as a motivation to introduce weak solutions, Lereo solutions. So let's talk about the scaling of the equation. Maybe let me add solve. Now, let's consider a solution UPF to the Navier-Stokes equation. Let us assume that it is regular. And given any parameter lambda positive, I'm gonna scale it as follows. So I define u lambda of xt equal to lambda u of lambda x lambda squared t. And I'll do a similar procedure for the pressure. I define P lambda in a similar way. and they'll do the same for the external body force. And here the observation is that U lambda P lambda F lambda is a solution to the Navier-Stokes equation as well. So the Navier-Stokes evolution is invariant under this scaling for every lambda positive. And the reason why this is kind of an interesting fact in view of the theory of classical solutions is because you can try to use this scaling to zoom in and try to control small scales. So in the end, solving the millennium problem or proving well-posedness for the Navier-Stokes equation has to do with the control on small scales. The heuristic here is that you have many competing terms in the equation. You have the diffusion part, which is essentially decreasing the energy and stabilizing the equation. So this is helping you in showing well-posedness. You have a term, a quadratic nonlinear term, which has an advection structure, and this is the main responsible for small scale creations. This term a priori might create small scales. And in the end, the game is try to understand in which regime the diffusion wins, and in such a regime you get well-posedness. In the regime where the nonlinear term is stronger, you have to find some kind of deeper motivation in order to show well-posedness. Now, coming back to the scaling, here the game is the following. We want to control small scales. If we have any a priori bound on the Navier-Stokes equation, think for instance to the kinetic energy, then in order to control small scales, we can try to zoom in according to the scaling and check what information we get at smaller scales. If you have an a priori control quantity which is invariant under the scaling or improves when you scale down, then it's very, very likely that you can prove well-posedness. Indeed, the quantity is controlled, you zoom in, it improves, so small scales have to be somehow controlled, and this gives regularity and well-posedness. The difficult situation is when the a priori controlled quantity you have instead becomes worse and worse when you zoom in. And this is unfortunately exactly the case of the three-dimensional Navier-Stokes equation. And this, if you want the mathematical motivation why it's very hard to prove well-posedness. Indeed, the best known a priori controlled quantity is the kinetic energy, the L2 norm in space, L infinity with respect to time. If you check what happens to the kinetic energy when you scale according to this scaling, you realize that in dimension 2 it is critical, meaning that the kinetic energy is constant. The kinetic energy of U lambda in dimension 2 is exactly equal to the kinetic energy of U. In dimension 3, the kinetic energy of U lambda is equal to lambda times the kinetic energy of U. This means that when lambda becomes bigger and you look at smaller scales, this kinetic energy is blowing up at infinity. Okay, and this is, if you want, the first motivation why there's some reasonable hope to attack the problem in dimension 2 with standard techniques. You control the kinetic energy, try to look at small scales, the kinetic energy is conserved, and you can play some analytic game. And indeed, this is exactly how the two-dimensional theory works. In dimension 3, there's no hope to apply this moral and get well-posedness out of this kind of arguments. Maybe I'll erase here. Now let's see a few examples of critical, subcritical, and supercritical spaces. So a critical space, now let's focus on dimension n equals 3. A critical space is a space invariant under the scaling of the Navier-Stokes equation. And easiest example, so you can check that L infinity in time, L3 in space is critical. And notice that the kinetic energy corresponds to L infinity L2. So we are a bit far away from the critical. In the general dimension n, the critical is L infinity Ln. In particular, n equal to kinetic energy. Another example is L infinity time h n over 2 minus 1, which in dimension 3 gives 1/2. That's another example of critical space. And more in general, in the class of Lebesgue spaces, we have an entire family of critical spaces. So if you put an LS integrability in time, LQ in space, you have to solve a relation S over 2 plus Q over the dimension of the space, which, let's write n, equal 1. And if I'm not wrong, you should recover L infinity Ln when S is equal to, oh sorry, is 2 over S. N over Q. Now when S is equal to infinity, yes, you get Q equal N. And we say that a functional space is subcritical if, when you zoom in, the norm decreases. And examples of subcritical spaces are L infinity, LT, L infinity in time, LP in space, with P bigger than the dimension. So in a certain sense, if you are more integrable than critical, you become subcritical. If you are less integrable than critical, you become supercritical. And easy example of supercritical space is L infinity LP, P smaller than the dimension. In particular, dimension 3, the kinetic energy, is supercritical. Now, what can we prove using these ideas and analysis of the scaling of the equation? Standard results for classical solutions. So essentially we have two classes of results. One about global well-posedness, when we assume some smallness on the initial condition. And smallness has to be understood in terms of a critical space. The other class of results is about local well-posedness, well-posedness in a certain interval of time, provided we have a priori controls on subcritical norms of the initial condition. Well-posedness for small data, and smallness is understood in critical nodes. Or local theorem in global. For generic data with bound on subcritical spaces. So just to give a sample statement, I'll write down two theorems. One is global composeness. So let's assume n equal 3. And let's consider initial data f and u naught classical, exactly as in the Millennium Prize problem. But then I want to assume that the L3 norm of U naught plus the L infinity in time, L1 in space norm of the external body force are smaller than epsilon. And this epsilon is small enough. There exists epsilon such that. Then there exists a unique classical solution. And you can also check that U and P are bounded and the kinetic energy is conserved. All the possible good properties you might think of hold true in this case. And notice that those are exactly critical norms. L3 is critical for the initial condition. L infinity L1 is critical for the external body force. You can check with the scale. Okay? So the message is simply smallness with respect to critical norms, the problem is solved. The Millennium problem is solved. Nice. Now, local well-posedness. So again, n equals 3, and f u naught classical. So what happens is that if you cannot ensure smallness in a critical norm, what you can find is a time scale, let's call it T star. And this time scale depends on some subcritical norm, any subcritical norm of the data. So for instance, we can pick U naught in L3 plus epsilon, and just going slightly above the critical threshold, and f in L infinity time, L1 plus epsilon space. This time is positive, just depends on the subcritical norms of the initial conditions, and you can find a unique classical solution in the interval 0 to star. Okay? So you can locally solve the Millennium problem, but you cannot ensure that T star is equal to plus infinity. So it might happen that something very bad happens at time T star, some blow up or something of course, and you lose the regularity and the well-posedness of the problem. I'm not going to prove these theorems, I just want to give some heuristic of why these two statements are true and why it's very, very hard to go beyond these statements using standard techniques in nonlinear partial differential equations. And the heuristic I'm about to tell you is from Terence Tao, and I think it's very, very nice. Maybe I'll move it here. Heuristic. So as I said, in order to show verbose, we want to take advantage of the stabilizing effect of the diffusion of the Laplacian, and we look for regimes where the Laplacian is able to beat the nonlinear term, which is the main source of small scales creation. Now, in order to understand the size of the various objects appearing in the equation, I'll make a lot of simplifications. So first of all, I'll drop the pressure, and I'll drop the external body force. I'll simply eliminate them from the equation. So let's simply drop them. Then I'll assume that my velocity field uxt is concentrated in frequency, meaning that all the frequencies of uxt are concentrated around a certain value n, depending on t. And I've also assumed that the amplitude of u, let's imagine that u is concentrated somewhere, in frequency is concentrated around nt, and in the physical space is concentrated somewhere, and where is it is concentrated, the typical magnitude, the typical amplitude is at. So I'm trying to describe a complex vector field by means of simply two parameters. Okay, it's just a heuristic simplification. Now, let's look at the remaining terms of the equation. So the nonlinear diffusion, the nonlinear advection, and the diffusion term. And I'll assume also for simplicity that mu is equal to 1. This is just a parameter, I scale it to be exactly equal to 1. Now let's look at the diffusion, at the size of the diffusion term. The diffusion term is Laplacian of u, which is of size, well, the amplitude is going to be a. And we are taking two derivatives, the typical frequency is n, so we get a n squared. Okay? Now let's look at the advection term. The advection term is one derivative of u squared. By the way, I didn't mention this, but you can easily write this as u dot grad u. This is because u is divergence free. Now it looks way more advection. And what's the size? Well, the amplitude is going to be the square of a, because you have the quadratic term, and you also have one derivative, so you are going to get capital N, right? So here the size is more or less a squared n. Now, in the diffusion regime is when this term is much bigger than this, right? And if this is much bigger than the advection, the equation becomes essentially the heat equation, and therefore we expect verboseness, and we expect to be able to control both the amplitude and the frequency. So once we enter the diffusive regime, we will stay in that regime forever, and we can solve the equation. So it's kind of natural to expect that Laplacian of u bigger than nonlinear term. So in terms of our parameters a and n, this amounts to, what is it? The Laplacian is a n squared, so n way bigger than a. So this amounts to a smaller than n, right? And here we expect that once we enter in this regime, so in particular if our initial condition satisfies this property, we are within this regime and we will stay in this regime forever and the equation is well posed. So we expect well posedness as soon as we enter this regime. But on the other hand, we have to take into account also the advection regime. And here is when the advection term is way stronger, and this is the case n way smaller than capital A. So what is going to happen here? Well, the honest answer is that we don't know. Here the equation is simply the nonlinear advection with the quadratic nonlinearity, and a priori this nonlinearity might create a lot of small scales very, very quickly, and for instance it can generate a blow up in finite time. But we have to balance the sides of the advection term with the time derivative. So if t is the typical time scale at which u oscillates, when we balance the equation, we have the time derivative should be more or less of sides u dot grad u in this particular regime. I dropped the Laplacian. But this is nothing but a over t is the magnitude of the velocity field divided by the typical time scale where we can appreciate the first important oscillation of the vector field u. And this is what I computed, a squared times n. So this means that up to t equal 1 over an, we have some control, thanks to the equation. But we cannot say anything about what is going on after this time scale. So after this time scale t, the vector field u might change, and we don't have any information about the quantitative or even qualitative information. All right. So in order to get well posedness, we need either to enter the diffusivity regime, and this is going to give global well posedness, we will stay there forever, or we are going to get some form of well posedness provided we look at local existence before the time scale, which depends on the magnitude and the frequency of the initial condition, is 1 over an. And now let's compute this. Let's try to compute some norm of a velocity field with that structure. So for instance, let's study the LP norm of the initial condition. And let us assume that we are given some bound on the LP norm. Now, what's the LP norm of a velocity field like this? Well, the LP norm is going to be the product between the magnitude and the volume of the support of the velocity field raised to the power 1 over t. But what's the volume of the support? It depends, but given that the typical oscillation, the typical frequency is capital N, at least the volume should be n to the power minus b. Right? I mean, I'm thinking of a function which is oscillating at frequency n, so in order to oscillate at this frequency, the support should be at least a ball of sides 1 over n, right? Or if you want, this is the uncertainty principle. So all in all, given the structure of our initial condition, what we expect is a bound of the form magnitude times n to the minus dimension, which is 3 in our case, over p smaller than p. So if you have this control, then you get this bound on the magnitude and the frequency. Okay? Which, if you want, you can think of it as a control of A in terms of n. Now, if you want to start within the diffusivity regime, what you need is A smaller than n. Right? But in order to ensure A is smaller than n, you want this to be smaller than n. Right? I mean, this is the inequality you have. If this is smaller than n, then capital N, done. So, to enter the diffusivity regime, you need B and 3 over P smaller than n. Right, which is B smaller than 1 minus 3 over P. So if you pick P equals 3, we are looking at the L3 norm. And the L3 norm is exactly a critical norm. And here what I'm saying is that, I mean actually here you want way smaller than. If you pick P equals 3, the condition becomes P way smaller than 1. But P equals 3 is exactly a critical space. And the condition P way smaller than 1 is nothing but being small in a critical space. So this is exactly the assumption of the first theorem over here. This is telling you that if you have a small initial condition in a critical space, for instance L3, then you immediately enter the diffusivity regime, and then you hope to solve the equation by essentially perturbing the solution to the linear heat equation. Okay? Alright, but imagine that instead of controlling exactly the critical norm, instead of having smallness in the L3 norm, you have some bound on the L3 plus epsilon norm. Or if you want, you have some bound in the LP norm with P strictly bigger than 3. What can you say? Let's see. This. So if P is the quantity, the norm you control is strictly bigger than 3, then again there are two cases. You might be lucky and fall in the diffusivity regime, and in that case, beautiful, you have well-posedness. Or it might happen that you do not belong into the inequality in order to get the diffusivity regime is not satisfied. And this is the case if A is way smaller than, if B and 3 over P is way smaller than N, again, this is diffusivity. And here we are happy. But let's consider the remaining case. The remaining case is when you have the opposite inequality. Now, we are not in the diffusivity regime, and we have to check the time scale t. We expect well-posedness in the time interval 0, 1 over an. But let's estimate this time scale. So we know that A is smaller than B times n to the minus 3 over t. This gives a lower bound. This says that t is going to be bigger than 1 over p n to the power 1 plus 3 over p. I'm just using this information. Am I right? So, yes, here I was wrong. Okay. But on the other hand, we know that n to the power 1 plus 3p is smaller than b, because we are exactly in the advection regime. So in all, you get 1 over p squared. So this is telling you that you have a uniform lower bound on the existence time scale, depending only on the upper bound on the LP norm, provided p is bigger than 3. So if you have an a priori bound in a supercritical norm, you get a lower bound on the existence time scale. And this is exactly the content of the second theorem. If you try to play with the supercritical case, so when p is smaller than 3, you get nothing. T can be as small as you like, depending on how big is the frequency of the velocity field you started with. Okay? Let me check. How much we have? 20 minutes. 20 minutes. Okay, so of course this is not a proof of these two theorems, but I think it's really the essence of them, and is essentially the essence of the well-posedness theory. Yes?
So you need the decay assumption with theorem, or just what's written in the theorem?
Say it again?
You need the decay assumption that you have
On the initial conditions? Not really. I mean, those are like the best assumption I mean, if you can just assume the L3 and L infinity L1 bound, and then get the solution, which is not classical because you start not so regular, but is at least a mild solution, and you can, I mean, you have a notion of solution, and the problem is, in the first case, globally well posed, and in the second case, locally well posed. So the essence is in this condition. Then,
I was confused with P, I guess that's because I'm not with, so do I have to think that I take the curve and then I bring P and I just solve for curve U?
I mean, I cannot hear you well because you're far away.
I'm always confused with the P, which is
The pressure, you mean?
Yes, which I have to find.
Yeah, I mean, you can prove that you can get first U, and then you can build P simply by solving the equation I wrote somewhere.
Should I think that I take the curve and I solve for curve U?
That's one way, but it's not. I mean, in order to prove these two theorems, I wouldn't take the curl, but you can use this formulation. Maybe let me write this down. It's going to be, I think, much more clear. Where is the eraser? So one way to get rid of the pressure is to rewrite the system as follows. So you first introduce the Leray projector, which is a mapping from L2 of velocity fields into L2 sigma, and I'm denoting by L2 sigma velocity fields with zero divergence. That's just the projection. I'm using that L2 can be written as an orthogonal sum of divergence-free vector fields and pressures. That's an orthogonal sum, and you have the orthogonal projection. Now, once you introduce this object, you can apply the Leray projector to the equation, and you can rewrite the equation as dtu plus this projector of the u tensor u equal nu Laplacian of u plus Leray projector of f. And P is a very, very good operator. It's of order 0. It enjoys all the LP bounds you might want, also bounds in the Sobolev spaces, and so on and so forth. And usually, the rigorous way to prove the theorems I stated is to first apply some Duhamel type identity and look for a fixed point. And the Duhamel type identity looks like this. So you have u of xt, is equal to the linear evolution, maybe let's put mu equal 1 again by scaling. This is the heat flow evolution of the initial condition minus the action of the heat flow on the divergence of u tensor u ds, and plus the term depending on, or also the speed, the term depending on the pressure. And now you can re-understand the moral of criticality, subcriticality, and competition between nonlinearity and Laplacian in terms of this quadratic form. So when you try to estimate this term, in order to kind of close some contraction principle or something, here you have the regularizing effect of the heat flow. This is helping you. But on the other hand, you are losing one derivative because of the nonlinear structure, because of the structure of the nonlinear term of the equation, but more than this, you are also losing integrability, because here you have a square. So the heat flow should be able to make up for the loss of derivative and the loss of integrability. And this is exactly the balance, and if you are in a critical space, these two are exactly at balance. If you are in a subcritical space, you have some room. If you are in a supercritical space, you cannot close the estimate. As simple as that. Okay? Good. Now, this is essentially all the morals in the whole heuristic in the classical setting. That's what we can do. And of course, we are very far away from solving the millennium problem, being very, very supercritical. And a natural way to proceed is to try to introduce less regular solutions, weak solutions, and maybe try to show global existence for them. And once we have global weak solution, try to understand their regularity, their structure, and so on and so forth. This is kind of standard strategy in analysis, right? And in this framework, the natural class of weak solutions is the class of Leray solutions. They have been introduced by Leray back in I don't remember precisely, but more than 100 years ago. And let me introduce them as a theorem. So consider initial condition, the initial vorticity in L2. Zero divergence, of course. And body force in L1 in time, L2 in space. So note the jump irregularity between the Leray theory and classical solutions. Then, theorem. So here we can take n equal 2 or 3. There exists U in the energy class, the one I mentioned at the very beginning when we looked at the energy conservation for the Navier-Stokes system. And the energy class is L2, L infinity time, L2 space, intersection, L2 time, homogeneous H1 in space. And this U is a distributional solution to the Navier-Stokes system. And the distribution of formulation here is pretty clear, just integrates by parts against smooth velocity fields, divergence free, and compactly supported in space and time. You can integrate by parts, the pressure disappears, this is just a Laplacian, you bring it on the other side, and this is kind of an advection term, so you can bring one derivative on the other side. And this formulation makes sense as soon as U is L2 lock in space and time. You just need to have U tensor U in L1 lock, as simple as that. So, in particular, if U belongs to the energy class, the distributional formulation makes sense. You get a solution, and this solution is weakly continuous with respect to time, weakly with respect to the topology of L2. So the mapping T goes to U T dot in L2 is weakly continuous. In particular, it makes sense to prescribe the initial condition because of this continuity, and the initial condition is exactly what you expect. U0 dot is our U0. And then we have not the energy balance, but the energy inequality. So this means that the kinetic energy at time t plus the dissipation term is smaller than or equal to the initial kinetic energy plus the work done by the force. So for classical solution we have the identity. Here what we can prove is just the inequality. And those solutions are global. And sometimes are called Leray-Hawkes because of the work by Hawke on bounded domains. He constructed the version of the resolution in bounded domains. Okay, so now we have global solutions, but we don't know much about the regularity. We just need that they belong to the energy class, and we don't even know that the energy is exactly conserved. There might be some strange dissipation appearing over here. And again, I don't think I'll have time to prove this theorem, just wanna share the main morals. It's actually, I mean, from the point of view of modern analysis, this is an easy result, but it wasn't back in the Leray times. And the idea is very easy. You first regularize the system, and the way to regularize the system is the following. So let's first write it as in the advection form. This is just a rewriting. Now, let's modify a bit the vector field U appearing over here. So epsilon is a positive parameter, and the epsilon is just some modification. Now, the system is very, very good because the bad nonlinearity is not so bad. When epsilon is positive, this is just a transport term associated with a smooth vector field. The vector field depends on the solution, but is very regular. So it's not surprising that you can solve this equation globally, and you get reasonably good solutions. You can do it in two steps. So you first solve it locally, and then you show using energy conservation that blow up cannot occur. And notice that this system has the very same energy identity of the Navier-Stokes equation. Indeed, when you integrate this against U, you get 0 exactly as in the case epsilon equal to 0. So here, if you have a good solution of this system, you have the energy identity. And the energy identity does not depend on the modification. So you can solve a regularized system. You have an a priori estimate in the correct class, the one associated with the energy identity. You just have to pass to the limit. You have enough compactness. You need to gain some compactness in time, but this is a matter of playing some Aubin, Lyon's lemma, stuff like this, pretty standard stuff. Okay. So we have solutions. What are the natural questions now? Well, first let's check the time. How much we have?
5 minutes.
5 minutes? Okay, I just mentioned the question I want to consider. The question is, are the resolutions unique? Imagine that we pick super good initial conditions, so we go back to classical initial data. Then we know that for a small interval of time, we have a classical solution. But on the other hand, we have a global resolution, at least one global resolution. It is possible to prove some weak strong uniqueness, meaning that if in a certain interval of time you have a strong solution, classical solution to the Navier-Stokes equation, and a Leray solution, the two have to coincide. So if you start with a good initial condition, there exists some time T star such that there exists only one solution which is classical, and all the Leray solutions have to coincide with the classical solution. But then it might happen that at time T star some blow up or something happens. You lose the classical solution, but you have the Leray solution. And how many Leray solutions you have? If you think of Leray solution as a way to continue after the blow up, it's kind of interesting to understand if there's only one way to continue after the blow up or there are many. And this question of uniqueness is actually very old, has been mentioned for the first time in 1951 by Hopf, and there's also a work back in 1961 by Ladizeskaya. And we have seen very few progresses till the last 5 years. And next time I want to state a non-uniqueness theorem under the assumption, with certain assumptions. And let me say, the question with F equals 0, with no external body force, is still open. We have a result depending on a special body force, and I'll elaborate more on this next time. And I'll also introduce the second uniqueness problem I want to consider about Udovich solutions and the two-dimensional Euler equation, and then I'll comment a bit on the connection between the two and recent progresses. Okay, thank you for your attention.
Thank you very much. Very nice lecture. We certainly have time for questions. Yes, please, go ahead.
Are there attempts to try to prove non-existence without?
Non-existence? I mean, in the setting of, you mean non-existence for the millennium problem? Because
probably under different assumptions, but...
I mean, what people try to do, so in the negative direction, if you think of the resolutions, the natural statement to prove in the negative direction is non-uniqueness, because you always have existence. In relation to the millennium problem, if you want to show that if you want to prove that the answer is no, the natural thing to do is to try to build a blow-up infinite time. So more than, if you want, this is a non-existence result of global solutions, which is nothing but a blow-up construction for classical solutions. But those are the two lines of, that I'm aware of, the two natural lines of to attack the problem in the negative.
Yeah, I was just thinking of, because, you talked about the different scaling regimes, and that it's kind of natural to think that there might occur some blow-up, so I think it's quite natural to try to construct them.
There are people trying, and there are also very interesting, very recent results about blow up at the boundary of the Euler equation, blow up of the Euler equation with certain initial conditions that are not classical but still pretty good. And there are results also in these directions, and they are all very recent.
Yes, please.
I have a question, antidote topics. The things you discussed on initial data, if you have stronger property, like the smooth and compact score, this is sort of
If you assume, you can even take F equal to 0, and you know to smooth, compactly supported, and whatever property you want. Still, if it is not small in some critical norm, the problem is open as well.
and you don't have any control over the support, how it grows in the time.
Again,
Physically it makes sense that you don't suddenly get into
you have this nonlinear advection, right? So once you create a lot of small scales, then the support might start growing very, very quickly. So I don't think there are a priori estimates on the size of the support. I mean, you can, again, in the subcritical or the diffusivity regime, you can get the usual estimate. So the equation resembles the heat equation, and you have the kind of bound you expect for the integration. But in the real nonlinear turbulent regime, I don't think you have any a priori control.
The only thing that people know is the smallness of the
I mean, yeah, it's sad to say, but yeah, regarding classical solutions, essentially one can perturb the linear heat flow evolution. This is what one can do.
Further questions, comments? Yes.
What are the main obstructions to kind of reach the analysis situation of the already equation just by taking u and u equals to 0? Like, please
That's an entire research field if you want. So try to understand what happens when nu is very, very small and get Euler solutions into a limit. I mean, at the qualitative level, you expect to find that when you send nu to 0, you get the solution to Euler, and this is true in almost every case. There are very interesting quantitative questions in this direction, and this is connected with certain notions like anomalous dissipation, zero flow of turbulence, and maybe I'll mention something next time. But I mean, understanding at the quantitative level this kind of vanishing viscosity limit is a very deep and not well understood question.
These really solutions are just constructed for the minuses, so when nu is positive.
Yeah, I mean, what I said today, all the statements were about Navier-Stokes equations. I'll say something about Euler next time. And of course, I mean, I've been talking for 1 hour about Laplacian versus diffusivity versus advection. And I mean, when you go to Euler, you have no Laplacian. So just have to play with the advection. Let's go.
Yeah, but you.
Yeah, that's a hard question.
You expect that it's when something is disappeared somewhere.
I think that, I mean, if you wanna build a counterexample to either no uniqueness and non-conservation of the energy, it's kind of should be. I don't want to say something which is not correct. So what happens? Maybe next time I'll give a few examples. So what happens is that the regime where you have non-conservation or conservation in general does not coincide with the regime where you have uniqueness, no uniqueness. And this happens already, yeah, this happens for, I mean, we expect that this happens for the Euler equation and for the Navier-Stokes equations. There are few heuristics suggesting what's the correct regime where to study energy conservation. I'm not aware of many heuristics suggesting the correct regime for uniqueness, but in principle they are different regimes. And I'll try to give precise statements next time about non-conservation, conservation. This has to do with Onsager theory, turbulence and stuff, but there are precise statements and theorems there. Regarding no uniqueness, not really.
Any final question or comment before we go for coffee? Yeah, let's take one more.
Could you repeat why in the heuristic argument the zero and is AN understood?
It's not like exactly what I say is that the LP norm has to be at least AN to the minus 3 over P, and the reason is that the LP norm is more or less magnitude times the volume of the support. The magnitude is A. What I'm saying is that the volume of the support has to be at least N to the minus 3 over P, where 3 is the dimension and P is the integrability exponent. And this is because if you have something concentrated at frequency N, in frequency, reasonably in space has to be, I mean, the supportive space has to be at least big as a ball of radius 1 over N.